So welcome to Information Theory Lecture 30. So I mentioned a couple of other things about the final project already, so I don't need to go through them again. But today we're going to talk, and we're going to finish the discussion about Lempel Ziv Compression. And one of the things I asked you to do before coming to class, hopefully, was to go through the beginning of the proof that we did last Wednesday and that you saw on YouTube. So hopefully everybody has gone through that beginning of the proof. And we can just sort of continue with minimal discontinuity between last Wednesday and today. And then if you're watching this on YouTube, of course, there's no discontinuity because maybe you finished that proof just 30 seconds ago. So I do have the new reading, so everyone should be reading the section on Lempel Ziv Compression in Chapter 13 of the book. This was not something that was assigned last time. There's no current outstanding homework, but like I said before, I'm going to add some additional assignments related to the final project and related to reading each other's assignments, reading each other's papers, and summarizing each other's papers. So this is something that, and I'd like to rotate them so that by the end of the class, everybody has read all of the papers. That's the plan. But I will offer more details as the assignments are created. Oh, this is old at this point. So we had our holiday. Did everybody have a good holiday? Did anyone go skiing or whatever one does on President's Day? Everybody stayed home and worked, right? That's what I did. So a little bit on the final presentation. So we're now actually done with, this is not very visible on the screen, but we're done with the February 17th assignment. We do have another assignment here. February 24th, and maybe if I do this, this will actually show up. Can you see that any better on the screen? Yeah. Okay, updated list of proposed papers, video based on feedback. It looks much better. Doesn't look much better on the computer screen. It looks great on the iPad. I don't know what's going on, but in any event, I will read it to you. It says, updated list of proposed papers decided based on feedback, updated write-up with more descriptions. And as I said earlier, there doesn't need to be any changes to the set of papers. So primarily what I want to see on Monday's updated write-up is progress. And then, like I said, there will be other assignments to read each other's papers. And then we have a couple of other deadlines up until the final presentation, which is Monday, March 17th, here in this room. And I will tell you how long the presentations are. It'll be like 15 or 20 minutes. We'll see, depending on how much time we have. Okay, so to review, so right now we are in the middle of this proof, but since for those of you in class it's been a week, let's just do a little bit of review. So remember, we came from the idea of Markov complexity, and Markov complexity does sort of give you this strategy for universal compression, where it gives you a code with a length, which is the program that generates the string, and that actually works perfectly well as a code word for any particular string you want, even though the code words have nothing to do with the probability. So we don't need, if we actually do Markov complexity, if we find the shortest program, that's a valid, if that was possible to do, that would be a perfectly valid string, irrespective of the probability. The idea of universal source coding, however, is the same. It's basically saying, is there some strategy so that we can compress a source down to its entropy without actually explicitly using the probabilities, and which can be algorithmic and based only on just the string itself. And it's not multipass like Huffman, where there's maybe a block of size n that you have to choose, and where you get the Shannon entropy if you set the block length very large. Nor is it like arithmetic coding, where you have to sort of repeatedly update a probability distribution based on conditioning of some sort. So Lempel Ziv is our method to do that. Is it one method? There are other methods as well. This is the one that we're going to study. We are studying. And so just to review, the idea is that we parse the sequence into phrases. This is the terminology we're using. And the phrases are such that each next phrase is the shortest phrase, or shortest subsequence of prefix of what has not yet been parsed, not yet seen. So we talked about this parse here for this is the thing. We could do it for any alphabet, like a binary alphabet. And for the most part, we're doing a binary alphabet. We can essentially represent an encoding by a table, where each parsed string consists of like two numbers. Here's the two number, and 5 and t. So 5 is a pointer back into the history saying what the prefix was, and then we have one new symbol. So every single phrase turns into an integer and a symbol. And so what we need in order to store this is essentially, bits needed to store the integer, which is log of something, where something is the number of phrases there are, and then the number of bits to store the symbol. And in the case of a binary code, it's just going to be 1. So we're going to have like 0, 0, 1 for the pointer 1 plus a bit, which is the new bit. So we talked about this idea of a parsing. I've already said this. A parsing is a division of the string into phrases, and a distinct parsing is really one where the phrases are identical, where no two phrases are identical. We define a couple of notational constructs. C of n is the number of phrases in a parsing of a string, of a Lempel Ziv parsing, LZ parsing of a string of length n. And so we're just using it as C of n, even though it really depends on C of x of n. This is really the dependence. The total length of the compressed sequence is this, and this is really important to understand because we need log of Cn bits to represent the pointer. Each pointer, we need 1 bit to represent each new symbol, and then there is Cn of 1. Right? So is this clear? Why this is the length? And so this quantity, this total length divided by n, is then the per symbol number of bits. Okay, and we want to show that the per symbol number of bits, when we do have an entropy, when we do have a stochastic process of some sort, we want to show that that converges to the entropy. And again, as I said last time, this is really an expected value construct here. Okay, so this is really taking the expected value over all probability distributions. This is a random variable. Or equivalently, you could say that for any real string that's drawn from this particular distribution, this quantity converges asymptotically to the entropy based on the weak law of large numbers. So that's the same thing. So this is the theorem that we are sort of in the middle of proving, I believe. So this is saying that the number of distinct phrases in any binary sequence satisfies this quantity. And we argued why this and this was the same. And so this basically means that it's upper bounded by n over log n, plus 1 plus something that goes to 0. Okay, so let's just briefly go over the part of the proof that we saw before. So nk, we're defining this value nk, which is the sum of the lengths. This is really important to remember. It's the sum of the lengths of all distinct strings of length less than or equal to k. Right. And then we can write that as this is just a simple identity which we use. It's just basically summing for L is equal to 1 to k of 2 to the L. We're going to use that. So nk can be written in this way. It's the sum of the lengths of all distinct strings. Right? Because the length is j and there's 2 to the j of them, and we're summing for j equals 1 to k. And we got this inequality here, or this equality here, so that we could actually just write this very simply in this fashion. Right? Okay. Now here's the tricky part, and this is where I wasn't sure everybody understood me, but basically we're considering two cases. We're considering, what we want to do is we want to show that C of n is upper bounded by n over, we want to show this thing, n over log n. This is what we're trying to show, really. This thing right here. Okay. So n is the length of the string. And we need to consider two cases for n. Either n is equal to nk for some k, meaning it's exactly equal to the sum of the lengths of the distinct strings of length up to and included k, or n is between nk and nk plus 1 for some k. Okay, one of those two things will happen. It's kind of like we mark these values nk plus 1, nk plus 2, nk plus 3, And either n is right on these critical boundary points, it's one of those nk's, or n lies somewhere in between. And what we want to do is then bound Cn for each one of these two possibilities. Okay. So then the question is that when you have C is the number of distinct phrases, and when we have a string that's parsed into distinct phrases, if we want to maximize, because we want to upper bound C of n, we want to come up with an upper bound on it. If we want to maximize that, we need to parse things into as short of phrases as possible. We can always parse it into, we could parse it into one distinct phrase of length n, but that would not maximize the number of phrases, right? That would minimize the number of phrases. It's just one, and it's distinct because it's the whole thing. But we want to maximize the number of distinct phrases, and so to do so, we make the phrases as short as possible. And so with that idea, if it's the case, case 1 when n is equal to nk, then what would maximize C? Maximizing C would basically say, well, we would use all of these distinct strings of length k, up to including k. So in other words, we'd use all of them. So n is equal to the sum of all unique strings up to and including length k. So basically, what distinct phrases would we use? We'd use all of them, right? And so how many of them are there? Well, the number of distinct phrases in such a case is certainly going to be upper bounded. We wouldn't. So why would we not use something more than k up here? Here's a question, sanity check. Why would we not use a distinct phrase longer than k in such a case? Because there would be fewer than them. That would not maximize the number of distinct phrases. Right? If we use one that's too long, it's just very similar to the case that if we use the entire string as a distinct phrase, that would mean that there's only one phrase. We want to maximize them. And when n is equal to nk, it's possible to fit all of them in there into a string of length n. Okay. So in such case, then how many distinct phrases are there at most? Well, there's at most this many, right? And from this bound that we had before, that's equal to this, minus 2. And then we get rid of the minus 2 and we get this. But now we use this equality and we turn it into an inequality by just getting rid of the 2. And that basically says nk is greater than k minus 1 and 2 to the k plus 1. So then we just solve for 2 to the k plus 1 here and get this inequality there. Does everybody see that? So that all I'm doing is basically, if I get rid of this 2, it turns this into what? It turns this into a greater than or equal to. And then I divide both sides of this thing by k minus 1, and I get this guy down here. But then this last inequality there comes from our case 1 assumption, which says that n is equal to nk. So this basically says that when n is equal to nk, C of n is less than or equal to n over k minus 1. So now what we're going to do the second case where n is between nk and nk plus 1. So we need to get a very simple way of going from nk to nk plus 1. And it turns out that if we add this bit to nk, we're going to get nk plus 1. So we had that picture last time where, does everybody remember the picture? Should I go through this again? I feel like I'm doing all of the stuff I did last time. Anyway, so much for reviewing the YouTube lecture. Never, ever, rule number 1 in teaching. Never end the class in the middle of a proof when there's a week gap between classes. That's a big no-no. And I will, of course, erase this from the YouTube lecture because I would never want my lectures to go on, online for the rest of eternity where I'm admitting to making a big no-no. Would I? No, actually, I won't erase it. You can go and listen to it. You know what I should do? The other thing I should do is add a laugh track. I think if in my lectures, whenever I made a joke, I added like a laugh track, a whole bunch of people laughing. I think that would make the lectures much more entertaining. But that's actually really easy to do.
You promised to add your own musical intro.
I will do that for my submodular class. I'm going to write a song. I promise you that I'm teaching a submodular class in spring. And I've already started writing a song that will be part of the musical intro for that class. And I will get a laugh track ready as well. That's good.
Do you know what would be really helpful is if you could get that class classified as one of the categories outside of the signal processing section of the, so it counts for a breadth course for signal processing.
Oh, submodular class?
Yeah.
No.
Is that possible?
I know. We can talk about that offline. That's very offline. That's not even like a bad joke. That's like a real serious issue. So anyway, so this is the gap between nk and nk plus 1. So now what we're going to do is assume that n is somewhere between these guys, right? So we have delta is the thing, delta is equal to n minus nk, and so that basically means delta is less than this gap. Here's the gap here, right? So should I draw the picture again? In case anyone's not clear what we're doing, I'll draw it quickly. nk plus 1, here's n. This is delta here, right? And this thing here is this quantity. It's basically k plus 1 times 2 to the k plus 1. Oops. So that's a picture, redundantly, because we did that last time. Okay, so how do we maximize Cn then? Because remember, we're trying to upper bound Cn, so we want to maximize it. What's the biggest it could possibly be? Well, first of all, we would want to make sure that we use, because n is bigger than nk plus 1, so we'd want to use up all distinct phrases less than or equal to k, right? Because that's the short. We want to use as many short ones as possible. But as soon as we use one of them, we can't use it again, right? So we have to move on to the next one. So we use up all the short ones, and because each time we use a short one, we use up less of the total string, which is a length n. So we want to use the short ones first. So we use up all the short ones. We don't want to use any phrases longer than k plus 1, right? Because that would be wasteful, right? Because n is less than nk plus 1, right? And nk plus 1 is equal to the sum of the lengths of distinct phrases up to and including k plus 1. And we don't need that. That would not maximize Cn. We definitely want to use all phrases length of every distinct phrase up to and including length k. And we have an upper bound on that already. We know that there are this many of them, right? We have this upper bound. And then we have this remaining. After we've done that, we have this delta, the n minus nk. We have this residual part of the string. So we've used up at that point all phrases up to and including length k. So now what we're going to do is, since we're not using length phrases, phase lengths greater than k plus 1, we're just going to essentially partition that string into phrases of length k plus 1. And how many of them are there? Well, there's the residual divided by the length. So there's that many. Delta over k plus 1 of them. So everybody see that? So then, what that means is that when n is between nk and nk plus 1, when we have this quantity, then C of n is upper bounded by this quantity here, which is the case. That's the first bit where we use up all phrases up to and including k, and then the next bit is where we use the residual. And then just writing that in a different way, we just make the denominator k minus 1 for both, which gives us this. But then that just gives us n over k plus k minus 1. Okay, so interestingly, the bound is very similar. In fact, the bound is exactly the same form. So for a given n, let's assume that k is in this realm, right? So k is just chosen so that it sandwiches n. What we want to do, however, is we have the upper bound on Cn in terms of n and k. What we want to do is bound it in terms of n only, right? Because k, we don't want to have k in there. So what we need to do is bound k based on n. Okay, everybody with me? Remember, n is the length of the phrase, length of the string, and k is the max phrase length. So we do have that n is greater than or equal to nk, which is equal to this, and that's greater than or equal to n, 2 to the k. So one very simple bound we have is this one, that k is less than or equal to log n. Right? The other thing we have is n is strictly less by assumption than nk plus 1, and we have this expression for it from before, right? And we can further upper bound it by getting rid of the 2, the free 2, and just doing k plus 2 to the k plus 1. And since we have this bound on k, we can turn that into log n plus 2 to the k plus 1. So we're just using this bound for k here. Okay. So what this means then is that we get one of these nice double log bounds. That implies that k plus 2 is greater than or equal to log over n divided by log n plus 2. Just this bound. Okay, so what we're going to do next is we're going to subtract 3 from both sides. Okay. Why? We'll see. So, and we're going to assume that n is greater than or equal to 4. So, I mean, obviously, we care about the asymptotic. So we can, if it doesn't work for 1, 2, or 3, let's just start n at some point where everything works. So let's just start it at 4, because that's what we're going to need. We don't care about the first 3 lengths, right? So when n is greater than 4, we can subtract 3 from both sides of this equation. So rather than k plus 2, we have k minus 1. So we have k minus 1 greater than or equal to log n minus log of log n plus 2 minus 3. And that's just basically from that previous equation, which is equation 30.9. Okay. But then we can remove a factor of log n from all terms. This is factoring out log n. And since n is greater than or equal to 4, we have that log n is greater than or equal to 2. So now this, rather than doing log n plus 2, since log n is greater than 2, it's bigger to do 2 log n. And making that bigger makes the overall equation smaller, since it's minus. And then once we do that, then log 2 of 2 is equal to 1. We just add it to the constant, which becomes 3. So we've got this whole quantity here, which I'm not even going to bother reading. But now we have a whole bound in terms of log n, because this whole thing, this whole bit here, can be made as arbitrarily small as we want by making n big. Right? Because log n grows exponentially slower than log n. I mean, it's just like, you know, if we have log n over n, that goes to 0. If we have log n over log n, that goes to 0. So that can be made as small as we want. So again, here's then using the min. Basically, this catches the case when n is not greater than or equal to 4. So epsilon n defined in this way goes to 0, then it gets big. So now what we have is, I mean, interestingly, we have a bound on k in terms of this thing here. It's starting to look familiar, isn't it? Okay. So we do have that k minus 1 is greater than 0, or equal to 0, right? So k is at least 1. And this is the bound we had before. But this is not the bound in the form that we want, because we need to get rid of k. So basically we use this bound here. We plug in this new lower bound for k minus 1, and we get this. And that's exactly what we want to show. Okay? So therefore, the number of distinct phrases, the maximum number of distinct phrases in a parsing of a string of length n is basically n over log n. Okay, so we're not done yet with this proof. We still have a little bit of machinery. Now this next thing is going to seem slightly tangential to you, but it's not. And this is something that we've already seen before, which is the maximum entropy distribution. But this is a slightly more general case of the maximum entropy distribution. So what this says is the following. Let's say that we have a probability distribution F and a support set S, such that if you integrate over the support set of the probability distribution, that equals 1. Right? So you can think of this as like a measure. S is a measure if you want, or you don't even have to think of that. And then you have a set of statistics, Ri. Okay, and for I is equal to 1m. So you have a set of m statistics, and you have a set of constraints that say that when you compute the expected statistic, you have to match these moments, alpha sub I. So there's, if I want to do this a little bit more carefully, I would probably do dx in there somewhere. Okay. So the maximum entropy distribution form, which we actually covered, says that basically a density, the solution to this, if we wanted to basically find the distribution F that has maximum entropy subject to satisfying these moment constraints, that density would have this form. E to the lambda 0 plus the sum factor of the 1 to m, lambda I plus Ri of x. So basically the statistics sit there in the distribution, and the lambdas correspond to the Lagrange multipliers, which then we can solve by duality, and we've already done a lecture on duality. We know what those mean now and how that works. And that's a unique maximum entropy distribution. So interestingly enough, all we need to do to find the maximum entropy distribution is to find these lambdas. The form of the expression doesn't change. And that's why sometimes this is called a maximum entropy distribution. It's also called sometimes a log linear distribution, because when you take the log of it, it's linear in the statistics, or linear in the features, if you will. Anytime you're using a log linear distribution, it's a maximum distribution subject to these constraints. So you're always doing maximum in some sense. Now, of course, you need to have the alphas to determine the constraints. And it's unique. And why is it unique? It's because the entropy is concave, right? Strictly concave. It's not like there are many distributions that match these moments, but there's only one of them that matches these moments and has maximum entropy. So we already said this. An example is the Gaussian. So in a Gaussian, we saw as the maximum entropy that it's the maximum entropy distribution having the first and second moments of the mean and the covariance matrix. Because the mean and the covariance are just two moments, right? The statistics are either x or x squared. For the scalar case, or the vector x, the identity, or xx transpose for the covariance. So, but any max entropy distribution is the same, whether it's a Gaussian or anything else. And so a Gaussian is like a log linear model as well. The usual normalization in the Gaussian, if you're wondering, is sort of within, sitting inside of lambda naught. Okay, so what we're going to do is use that property to sort of sketch the proof of the following, which is something that we actually need for the Lempel Ziv proof. So when z is a positive integer valued random variable with mean mu, then we can have a very simple bound on the entropy, just in terms of the mean, as follows. So basically, the entropy of that positive integer valued random variable is going to be no greater than mu plus 1 log mu plus 1 minus mu log mu. So just from basically what we just said in the last slide, how do you think we would prove this?
Comparing that to a Gaussian?
Is a Gaussian a positive integer valued random variable?
No. Comparing it to...
I mean, we're not going to go through the mathematical mechanics, but the intuition of the proof, I'm hoping that everybody can see right away, even without going through it. So a maximum entropy distribution is a distribution that has maximum entropy satisfying a certain moment constraint. So in order for this proof to be easy, it must be the case that this thing on the right is the resulting entropy of this maximum entropy distribution. Right? So basically what we'd say, okay, what is the maximum entropy distribution of a distribution that's defined on positive integers? And what is that entropy? Which means that since it's maximum entropy of all positive integer distributions having a mean mu, that's all we need to do, right? And so it turns out that a geometric distribution is a maximum entropy distribution too. So a geometric distribution is defined on the positive integers. It's p of z is equal to 1 minus p to the k. Sorry, there's a typo there. This should read k. K there. So the probability of z is equal to k is equal to 1 minus p to the k times p. Its mean, you can easily compute, is just 1 over p. And it turns out that that is, it's got entropy equal to mu plus 1 log mu plus 1 minus mu log mu. Okay, so we've got its entropy, we've got its mean. What's the last step? The last step is to show that that distribution is the thing that results from this maximum entropy computation. Okay. So how does this look like a maximum entropy distribution? What you'd have to do is do, e to the log of this thing, and then you get it in that form, and then that would be the result. So basically what you'd get is e to the k times log of 1 minus p plus log of p. And that would be the distribution. So that's something that can be obtained just by using Lagrange multipliers and solving. Like I said, I'm not going to go through the math, but if you'd like to do an exercise, feel free to do it. So basically what this means is because the geometric is the maximum entropy distribution, or positive integer variables, any distribution that matches this moment, namely the mean mu, can't have entropy that exceeds it. Okay? So that's just a little trick. Anytime you want to find an entropy bound for some distribution on things, just find the maximum entropy distribution. If you know it already, you know what form it's going to take, e to the lambda naught plus the sum. Maybe it can be simplified, and maybe it turns out to be an existing family form. In this case, it's a geometric. Okay, so the next bit is ergodicity. So this is something that I think you should have learnt about in 508. Is that right? Has anyone taken 508 or 505?
What's 508?
I don't know. Something where you learn about ergodicity. No, I'm joking. I think it's stochastic processes part 2. 505 is stochastic processes part 1. Well, let's just talk briefly about ergodicity. So the basic idea is that ergodic, by the way, all of these theorems that we've been talking about correspond to stationary ergodic stochastic processes. And what we really want to do is show that this thing converges to the entropy rate of a stationary ergodic stochastic process. And let's just sort of briefly just get a little bit of intuition about what ergodic is, or what ergodicity is. The basic idea is that the persistent behavior of a stochastic process is such that it exists forever. So there's no partitioning into different sort of persistent modes of behavior. And as a result, what means, and the consequence of this is that what we usually always assume, is that time and ensemble averages are the same. So let's say that x is a sequence of source letters, and we're going to define a time shift operator. So t of x, TL of x, is going to be taking the sequence x and shifting it in time by L, forward or backwards. L can be positive or negative. So in other words, if we define t of L of x to be equal to x prime, then basically x of I is just equal to xi the ith position of xi is just equal to the I plus lth position of x. So it's just time shift. Now, what we're going to allow S to be is an infinite set of sequences of source letters. So X is an ensemble of sequences, each sequence of which is infinite. So it's an infinite set of infinitely long sequences. Okay. And so what we can do is then apply the time shift operator to this set, and what that does is it shifts every single one of the infinitely long, every one of the infinitely many infinitely long sequences in S by L positions. That's how much it shifts it. So that's basically saying this. So if it's the case that x prime is equal to a shifted version of x, and if x prime is in the shifted set, then that must mean that x was in S. Okay. So the notion of invariant, so an invariant set of sequences is one for which we don't change it when we shift it for any L. So here's an example. The set of all sequences of a discrete alphabet source is invariant. Right? Think about all infinite sequences of some discrete alphabet, like all infinite length binary sequences. The set of all, obviously it's a very big set, but if we shift it, we're not going to change the set, right? Here's an example where we have a finite set of sequences. Maybe it's a little bit easier to comprehend. This is a finite set, but on the other hand, it's still invariant because it's just two sequences. They're all 0 and they're all 1 sequence. And so if we shift these guys by any amount, they're not going to change. Here's another infinite set of invariant sequences. We take any sequence and we shift it in all positions and create a set by itself shifted in all positions. Then if we shift the set, we still have the same set shifted in all positions. So this is an invariant set. Yes?
When you say you're shifting the set, you mean you're shifting each element?
That's right.
In the set? Okay.
That's right. So that's what this means. When we shift the set, then that means that if x prime is a shifted version of x, then whenever it's the case that x is in S, then x prime is in the shifted version of the set. So this sequence, the set of all shifts of a single sequence is an invariant set. And this is an infinite set of sequences. Okay, so a discrete stationary source. So now we have a probability distribution over sequences, right? And we can actually, and it's a probability distribution over infinite length sequences. And for any given sequence, we can ask for its probability, and we can ask for the probability of a set of sequences, basically by summing over the, these are disjoint events, and we can sum over the probability of each of the sequences. And so what in a discrete stationary ergodic source is one where basically invariant sequences either consume all of the probability or have none of the probability. So there's only one invariant set of sequences. So there's only one persistent mode of behavior. Okay. So that's really the definition of ergodic. Like by shifting stuff, the sequence, you don't change things. So what that means then, I was actually going to go through this proof, but I thought that would lead us a little bit astray. But this property alone basically means that we can take time averages, ensemble averages, and assume that they're the same. Or prove that they're the same. This is a great book, by the way. If anyone hasn't ever read this book, this is the book I think we should be using for 508. And if you haven't read Grimmett and Sturzacher, then you should go out and buy a copy and read it. It's something that I think everybody who does time series analysis should read. Is there a question?
Yeah. So What's an example of an invariant set of sequences that is probability 1, and what's an example that has probability 0? So I'm just trying to understand.
I'm just saying that like you can basically partition all sequences into these different persistent sets, right? And what an ergodic, stationary ergodic probability distribution is one for which only one of those persistent sets has any probability, and it has all of the probability. The other persistent sets don't have any probability.
Okay. So out of all invariant sets,
right?
So you got a big set.
Like let's say that here's a set of all sequences. Mm-hmm. Let's partition them into persistent sets.
And persistent.
What's the definition of persistent? Did we just define that here? Oh, sorry, invariant.
Oh,
that's
invariant.
Invariant. Did I say persistent? Yeah, sorry, invariant. Every invariant, there it is, I'm reading it wrong. So every invariant set of sequences has all the probability. So what we're doing here is we're partitioning the set of all sequences into different invariant sets. Persistence is kind of the same thing, isn't it? But every invariant set, right? And what we're saying is that only one of them has any probability, and it has all of the probability. So now we're going to start with a stationary ergodic process with probability mass function, as given as follows. So remember, we're still going to use this stuff to try to prove the Lempel Ziv thing. Let's find a kth order Markov approximation to this. So it's not necessarily a Markov process, but we're just going to use this for the purposes of computing the stochastic process and showing. The reason for this is, remember that when we talked about this last quarter, and we talked about the entropy rate of h of I given, h of x of I given x of 1 through I minus 1. And if we let I go to infinity, that's equal to the average, the entropy of x of 1 through I divided by n. Nobody's disabled that bell yet. So we had this, let me just write it down. We had that h of x of I given x of 1 through I minus 1 was basically the same as h of x1 through x of I divided by n. So that asymptotically, these guys are the same when we have a stationary stochastic process. So we're doing this sort of kth order Markov approximation by saying q sub k, let's use a different color here, is defined by this probability. So notice here that we're starting, this is a little bit tricky, so I'm going to go through this carefully. We're starting here at x of negative k minus 1 going up to x0, and then we have all of these new symbols. So this is kind of like the previous state, right? And that previous state corresponds to this bit here. Okay, and basically it's saying that since it's a kth order Markov assumption, it's saying that the probability of xj given everything else is probability of xj given the preceding k states is independent of everything earlier. So the preceding k symbols is sufficient to render everything earlier independent of xj. That's a kth order Markov chain, right? So therefore, in the kth order Markov approximation, we've got this whole expression. This whole expression here. Everybody's happy with this notation, right? Just want to double check. This notation here. This doesn't make sense, and none of that will make sense. Okay. So this kth order Markov chain is stationary and ergodic as well, since the original thing is stationary and ergodic. And that's something that we know. So then what we end up getting is the following. So if we look at the negative negative average log of the n states. We can write this as in this fashion. We're conditioning on sort of the initial state, the states going from negative k minus 1 to 0. So this is going to start looking like an entropy rate. In fact, it is an entropy rate. This thing converges when n gets big to this expected value, thanks to the weak law of large numbers, which is exactly equal to the conditional entropy. Okay? And we saw that last quarter. So what we want to show then, and what we're going to show, is that the Lin sup of this quantity, remember this is the total number of bits that's necessary for the Lempel Ziv encoding divided by n, and so therefore the whole thing, the Lin sup of this quantity, which is the average number of bits per symbol that we're going to need, is upper bounded by this entropy, conditional entropy, which converges, as we know from last quarter, to the entropy of the stochastic process, which exists because it's a stationary ergodic stochastic process.
X is the stationary process that we're encoding using Lempel Ziv.
Yeah, we use this notation to correspond to the entropy rate of the stochastic process, which last quarter we said was the same. It's those two things that are asymptotically, these things, the stuff that I drew. Both of these guys converge to h script x. This guy converges to h of script x as well when n gets big. And that's what we did last quarter. We talked about stochastic processes, of entropy of stochastic processes. So what we want to do for Lempel Ziv is show, because that's the thing that makes most sense. We're not saying that the process is independent. It's not a set of IID random variables. But what we do have the notion of a stationary ergodic stochastic process. We have the notion of the entropy rate of a stationary ergodic stochastic process. And so for this to make sense with respect to entropy, we need to sort of show that it converges to some notion of entropy that we already know, and we know this in the stationary ergodic case. If the process is not stationary and ergodic, then you can imagine that if there are if the stationariness is not changing too rapidly, that we sort of trail the entropy rate, like maybe there's sort of a local entropy here and a local entropy there, and it's sort of the same kind of time frequency trade-offs that you always have in signal processing. If it changes too rapidly, then the Lempel Ziv is not going to catch up quickly enough, and it's not going to sort of memorize nice strings. But in general, it's as long as it's if it's stationary ergodic, asymptotically the Lempel Ziv will, as we're about to show, converge to the entropy, meaning the number of bits per symbol. And we have an expression for the number of bits per symbol, this thing on the left. This stuff. Now there's also the 1, right? But we're going to see that doesn't matter. Okay. So we're going to. So before we actually show this, let's do a couple more mechanical things. I apologize. Lots of mechanics here. So we're going to consider this string x of 1 through n parsed into c distinct phrases. So x of 1 through n is going to be parsed into y1 through yc, where yi is just a subsequence. Right? So c, remember, is the number of distinct phrases. And this is really critical to remember. It's distinct phrases. So in a couple of slides, I'm going to say, remember we said it was distinct? And I'm going to refer back to this. It's distinct. And v of I is the index of the start of the ith phrase. So that basically means that we can use vi to give us yi as an index. So vi is a set of indices. And if we go, if we start at vi and end at vi plus 1 minus 1, then we get y of I back. So just vi is just defined so that we can get y of I. And then we also, this is a little bit of an overload like of notation, but S of I is going to be the preceding k symbols, or the k symbols preceding yi. So this is going to be like a state, what we're going to be able to condition on. And since it's a kth order Markov chain, we're going to say if we condition on S of I, we don't need to condition on anything earlier than that. So remember, x is a string. The y's are substrings. The v's are indices. And the s's are substrings, but the s's are going to be the length k sequences that immediately precede the ith y. So si is this length k. So I guess, let me draw a picture. So here's x. Okay, so here's maybe yi, and here's, oh, no. See, I'm already screwing this up. How are we going to do this? This is the string x, okay? Here's a little substring. Let's call this guy yi. Okay. The starting point is vi. The starting point of the next guy is vi plus 1. And then we have a little length k, s of I, with the length of this string s of I is k. Did I leave anything out? I don't think so. So these are the indices. X is a long string. Yi is a substring. Si is another string, which is always a length k. Yi might not be a length k. Everybody got it? Got the notation? As best as possible? So now L is going to be an integer from 1 to n, and S is going to be some length k string. Okay, for L is equal to this integer, and S is equal to length string, we're going to define this quantity, CLS, to be the number of phrases in the string X with length L, and that have preceding state S. So going back to this picture, so yi is a string that has s of I as a prefix, right? Or not as a prefix, as a state, right? If that same s existed here, if this was s and that was s, and this string, whatever that y was, if that happened, if this y and this y were both of length L, then they would both contribute to CLS. Okay. So CLS is the number of phrases of length L with prefix S. I guess prefix is not really the right word, is it? I shouldn't use prefix. It's really state, because the prefix usually means that it's part of the string L. So it's part of the string Y, but it's not a prefix of Y. It's actually the stuff that comes before Y. So here's yeah, that's right. So it's like it's the stuff that precedes Y. So prefix, I shouldn't use prefix here. Okay, so here's a formal mathematical definition of CLIS. Basically, it's like the count of I, so I for all possible phrases in the string such that its length is L and its state is S. So therefore, if we count up over all, if we sum over all L and over all strings of length K, S, of C of L, S, then we just get equal to C, which is the total number of phrases in the distinct parsing that we've got. Okay. And furthermore, if we take this sum, we sum over all S of L times C of L of S, then we actually get the total string length. Right? Because we're summing over all strings of length L, and it says L times the number of them that have prefix S, and then we're summing over all prefixes S, all possible prefixes S, so we're going to get N. And so because of that, we can actually turn that into a probability distribution. And that's going to be the key to how we answer the following question. What we want to do is we want to sort of relate the probability of this stochastic process to some deterministic aspect of the parsing, right? Which sounds, again, amazing. So you're going to see Ziv's inequality is the key. That's the link. That's the missing link. That's the critical inequality in all of this. And obviously the bound that we saw before was important. But this is sort of the intellectual gap. This bridges the intellectual gap between these combinatorics and the probability distribution for any distribution. This is what we've got. Ziv's inequality. It basically says that for this stochastic process, and for any distinct parsing, which includes the Lempel Ziv parsing of the string, we have this probability bound. So the log of the probability, which is basically the probability of the string given S1, its first state, is upper bounded by this sum quantity, which is basically only related to properties of the parsing. So notice that the bound, and this is how the universal, this is the bridge of the gap between universal and non-universal. Here we've got universal on this side, here we've got non-universal on this side. Here we've got the probability distribution, here we don't do anything with the probability distribution, it's just parsings, distinct parsings. And so to prove that a universal scheme for data compression is in fact universal, we need to somehow bridge that gap, where we get rid of, or we don't use, or we bound the probabilities. So I've sort of said this. The bound is independent of Q and depends only on these counts, which is based on whatever the current distinct parsing is. And I guess another idea, maybe intuitively, you could say, maybe this will help try to understand this bound. It's saying that, in some sense, when we have more distinct y's, we increase these counts, and so therefore we make the bound smaller. So the probability becomes, the upper bound becomes smaller as we add diversity to the distinct parsings of the string. So maybe that kind of makes sense, that as soon as we see more different things, that's going to kind of, if we see lots of different things, then that's kind of like an increase in entropy, right? Because it's saying, well, if I always see the same thing, it basically means it's a fairly low entropy distribution, meaning that the thing that happens has a high probability. If we see lots of different things, maybe it's more like a uniform distribution, where we see this, and then we see this, and we see this, and we're going to see lots of a big diversity of things. All kinds of things are going to happen. There's going to be a lot of diversity, and that means that it's more like a uniform distribution. So all of the probabilities, or the max probability, is going to be smaller. So maybe that kind of makes sense. So to prove it, we're going to write it in this parsing. So we write the probability in terms of the parse here, which then means we can write it in this fashion. The probability for I is equal to 1 to C of the probability of yi given Si. And this follows from the Markov assumption. Right? So we've got S of I, and it depends on nothing else in the past other than the immediateness of I. Okay. So what this then gives us is, when we take the log, we get the sum. And so now what we're going to do is this sum over I, we're just going to say the sum over all lengths and prefixes, and the sum over all of I such that the yi is of that length, and prefixes such that S is equal to S of I, and we get the same thing here, or we have the same thing. Now we're going to multiply and divide by this constant within the sum. So we're going to multiply by 1, which is equal to CLS divided by CLS. Okay. But now we're going to use, what do you think? We're going to use Jensen's inequality. So how are we going to do that? Well, because this is a mixture. Because when we sum over all I such that yi is equal to L and Si is equal to S of this ratio, that's equal to 1. Because the number of terms in that sum is exactly equal to the number of strings of length L that have prefix S, or that have state S. So the number of terms is exactly equal to the definition of CLS. And we're taking 1 over that. So that is equal to 1. So we can treat that as a probability distribution. And because it's a probability distribution, we can then apply Jensen's inequality to this part here. So the expected value of the log is equal to the log of the expected value. And here's the log of the expected value. It's a concave function, log is. Okay, so now that we've got that, we still have this quantity to deal with. And the yi's are distinct. Remember I said that we need to use the yi's are distinct. So that basically means, look at this sum here. All of the yi's are distinct. So it's never the case that we're summing over 2 yi's that are the same. The other thing in the sum is that all of the si's are equal to s. So we might as well just turn this into an s here, right? And so basically we're summing over all of these yi's that are equal to L, and if we sum over all yi's, we're going to get 1, right? So this is definitely an upper bound, so we're going to get 1. So therefore this whole thing, let's erase it now that I've added stuff here. This whole thing has as an upper bound 1. This whole thing here has an upper bound of 1. So what we end up getting is the following. Here's the log of the probability. Here's the upper bound that used Jensen's inequality. And here's this last upper bound that used this property here. Hence, no matter what this probability distribution is, probability of that length and strain condition in S1 is upper bounded by this, which is based only on a distinct parsing of that string. Algorithm meets probability, or algorithm trumps probability, or algorithm bounds or dominates probability. So this is a pretty interesting thing, I think, because this is. You might think this, intuitively you might at first think that this kind of thing is not possible. But in fact it is. We just proved. So again, you might wonder, why are we going through these details of the proof? Because again, when you look at a proof, when you look at a theorem that seems counterintuitive, those are the proofs you want to go through. Right? Because they provide you with novel insight. Proofs that are obvious. If you're reading a paper, if a proof is obvious to you, it's not as important to read through the proof as those proofs that are counterintuitive. But then on the other hand, when you look at it again in this other fashion, in terms of the diversity, more diversity means higher entropy, and higher entropy means lower probability, and then maybe it is actually in fact intuitive. So. The next slide comes from lecture 26, as I said. We had a technical hiccup during the break again. So this is again a review slide on what lim sup means and how it's different than lim. This is something that we reviewed last time, or actually lecture 26, but we talked about how, for example, this limit doesn't exist, but the lim sup of sign does exist. It's basically sort of like the limit of the supremum, which is a very loose way of defining it, or more precisely, you define it as the infimum over n greater than 0 of the supremum for k greater than n of some sequence. So the sequence can be oscillating and it might not ever have a limit, but you're taking these supremums, so it's the infimum of these sups. Okay? So what we want to show then is the following, is that we're not saying necessarily that the limit of the sequence exists. What we are saying, what we are proving, is that the lim sup of the sequence exists, and that it converges to the entropy with probability 1. So the main theorem is that if X is a stationary ergodic process, and it does have an entropy rate, H, and Cn is the number of distinct phrases in a parsing of the sample of that length, then we have this bound. Okay. So what we do is we're going to write C for C of n and then use Ziv's inequality to right away just write this probability in this fashion. Okay? And by adding, or I guess by multiplying by 1, so we've multiplied, I guess we're doing 2 multiplies by 1 here. So we're doing, zoom in here. So we've got C over C, which is 1, and we're also going to multiply C over C here. So once we do that, we can write it out in terms of this form. And the reason why we're going to do that is because C is going to allow us to treat, as we're going to see, it's going to allow us to treat this as a probability, these guys as probabilities. And that's going to turn into an entropy quantity. Okay. So in fact, let's define this probability distribution in terms of pi. So pi ls is equal to C ls over C, which is this. And we can treat it as a probability. The reason why is because if we sum over all of s of pi ls, this is going to equal to 1. Remember, if we did it in terms of C ls, we got C, and so we just divide by the thing that we sum into it, and we turn into a probability distribution. So then, if we then take, in some sense, the expected length with respect to this distribution, we're going to get n, right? Well, not the expected length, it's really like the sum of the length. So therefore, the expected length with respect to the distribution is n over c. Okay. Does everybody see this? Why this is the case? This is basically summing over all of ls. So it's CLS again is basically the number of phrases of length n that have state s, right? In a parsing, in a unique parsing of a string of length n. And what we're saying is like all in that sum, we're summing over all phrases that have state s, and CLS is the number of them that have state s that are length l. We multiply them by l, and then we sum over all l, we're going to get back the original length of the string, which is n. Okay? And then if we just divide that by c, we're going to get n over c. So now we're going to just define random variables according to this distribution. This can be thought of as a joint distribution in terms of u and v, where the joint probability of u is equal to l and v is equal to s is just given by this pi value. And then we can marginalize out s. So this is basically, what is the meaning of this thing here, pi l? You guys tell me. This is a sanity check. So marginal probability, yes, it's the relative number of strings that have, starts with an L. Relative number of strings that have length L. So it's the probability, if you think of it as the distribution, it's the probability of L, probability of string that has, in this unique parsing that has length L. And so U is this guy. So E of U, the expected value of U is the random variable that has distribution according to pi val. And this is just the expected value. EU is just going to be n over c. The expected value of string lengths, not surprisingly, is just n over the total number of substrings. Right? That's not surprising. Now what this then gives us then, going back to this expression here, going back to this one here. So with this distribution, we can turn that into an entropic quantity. Basically, we've got Ziv's inequality gives us this, and then writing it in terms of that other form that I just highlighted allows us, and then using the entropy form in terms of random variables u and v, it gives us the following. It gives us c of h of uv minus c log c. So what do we have? We have this quantity. We have this is essentially the bound that we have. So we have, on the one hand, we've got the quantity we want. It's the entropy rate. If we set k to infinity and n to infinity, if we let k and n go to infinity, then it turns into the entropy rate of the stochastic process. Because as k gets bigger, it's no longer, it becomes less and less a problem to make the k Markov assumption, right? k goes from infinity to n go to infinity, it's no longer a Markov chain. It's just any stochastic process, any stationary ergodic stochastic process. Okay. And secondly, this guy is the thing that we want to show converges to the entropy of x. Right? This is the thing that we want to bound. And so this last guy here, we want to show this guy goes to 0. So the rest of the stuff that we need to deal with is going to be working on this right-hand side bit. Now, first of all, we know because it's an entropy that we can upper bound the entropy of the joint by the sum of the entropys of the marginal, of the two probabilities. It's a modular upper bound on the entropy. We also have another entropy, we have an upper bound on the entropy of V under the uniform distribution. Right? It's strings of length k. Under a uniform distribution, its entropy is just going to be equal to k. Okay? Now, by this other lemma, so remember the lemma that gave us the upper bound on the entropy of a positive integer random variable that we achieved by looking at the maximum entropy property? So U is going to be one of these distributions. U is a random variable on positive integers, right? Remember, U is it's corresponding to the lengths of these strings. It's a marginal distribution, so therefore it also has an upper bound in terms of that quantity. And the quantity is taking the expected value of U. So this is the entropy of a distribution. This is the entropy of the maximum entropy distribution with that mean on positive integers. Right? So we're using that upper bound. And I'm thinking the rest of this is just algebra, so I'm not going to go through all this stuff. So we get this inequality and this equality, and we get all of this stuff. And I just don't think it's worth going through all of this stuff, unless you want to. What do you think? So we go through every bit. This is just algebra. It's not even. It's arithmetic. So what we end up getting, what we do get, what's important is a bound on h of u. Can you believe I typed in all of this stuff? Today's lecture is admittedly a bit algebraic, but like I said, I think that the proof is important to go through because of the strange, counterintuitive nature of the proof. So, what's going on here now? Okay. Also having lots of technical failures. So what we want to do is bound this quantity. We want to show that this thing goes to 0. So we upper bound it. We can show an upper bound goes to 0 in terms of h of v and h of u. And we get this massive, complicated expression in terms of the algebra that we just skipped. A little bit more algebra, a little bit more algebra, a little bit more algebra. A lot of this stuff goes to 0 pretty obviously. This bit goes to 0. This bit we're going to see goes to 0. This n gets big. And the last quantity, we have this part here also obviously goes to 0 when n gets big. This quantity here, we need to look at that. Now we have this bound in terms of C of n. This is where we're going to use this bound. So remember, the bound basically says that C of n is n over log n 1 plus 01. And then if n gets big, that's going to be upper bounded by n over c. Right? Because log n eventually is going to get bigger than c, which is going to make that n over c bigger. Right? And then this final quantity, c over n log n over c, which is this part up here, this guy peaks at n over c. We can essentially use this upper bound here. So we're going to use the upper bound for c here. There's just this, and then the upper bound for c there. Because of its quantity. Upper bounding there. And then this is again more algebra, where we just rearrange things a little bit and cancel out common n terms. And the whole thing ends up turning into an expression which lives in the family log n over n. And that's something that goes to 0 as n goes to infinity. So basically what this means is that this bit also goes to 0. That's also O1. Yep.
We substitute for C both in the denominator and denominator. It's upper bound, right?
Yes, and the reason why that works is because of this monotonicity. Okay, up to this peak. Normally you can't do that both in the numerator and denominator, but you can do that as long as it's monotonic, because it's going to be, as long as we're doing that up to that particular point n over c. Normally you can't, obviously you can't do that. Other questions about that? Okay, so we get that this whole thing goes to 0 as n goes to infinity. And therefore, this quantity is upper bounded by the probability plus this epsilon guy, which also goes to 0 as n gets big. All that stuff goes to 0. And last thing we have to deal with is the k, right? So when we take the lim soup, I mean, we have, that basically means that we're going to have this upper bound, which we know equals to the entropy rate of the stochastic process when it's stationary ergodic. And thanks to the stationary ergodicity, if we let k get big, it turns into the entropy rate of the stochastic process. And that gets rid of the k. So then, relating this back to the overall length, so if we've got this stationary ergodic stochastic process, and then L of x of n is going to be the code word lengths for these n symbols, and we want to show this quantity. So we know that this is the actual length, right? So it's Cn times log Cn plus 1. This is where the plus 1 comes in. Again, so that's the actual code word length. And we want to show that that divided by n. So in other words, the Cn over n doesn't hurt us. That's the worry, because we haven't done that part yet. Because we still have Cn plus 1 divided by n, and we need to make sure that that goes to 0. But then Cn over n, if we take the lim sup of Cn over n, that's just going to get rid of the, remember it was n over log n times 1 plus O1. And so that's going to cancel out the n, and so we get this quantity. And my iPad just crashed. Pause the lecture. Are we crashing? We're not crashing. Okay, good. So I want to get to the end of this topic before we run out of time. So we're not. So this Cn over n doesn't hurt us, which is very nice. And so therefore, what we've got, putting everything together, is that when we take the lim sup of the Lempel Ziv length, the per symbol number, length. This is L is the number of bits in the encoding, and N is the number of symbols. So this is the number of bits per symbol. Then that's equal to this, which we know converges to the entropy, and this, which we now know goes to 0, and that's going to be less than the entropy rate of the stochastic process. So here's the consequence, and all of this work that we've done, and hopefully not flubbed too badly, is saying that this purely algorithmic procedure, the Lempel Ziv procedure, when given a stationary ergodic stochastic process governed by some distribution, even though this Lempel Ziv doesn't know anything about the probability distribution, it's purely algorithmic, it just memorizes strings, it basically will converge in the limit to the entropy rate of the stochastic process in terms of encoding length. So this is true instance of universal source coding. Okay. Just like Kolmogorov complexity. But this is realizable. I mean, you could actually code this up. In fact, it's very simple to code up. And it's used in gzip. So when this algorithm came out, when this was first published and discovered, it created quite a stir in the information theory community. People knew, hope that there would be a universal coding strategy. This isn't necessarily the best. It doesn't necessarily converge to the entropy rate as quickly as it could. It doesn't necessarily track non-stationary stochastic processes as quickly maybe as other methods could. That doesn't mean that it's the end-all, be-all of compression methods. And in particular, for any finite length source, it's not going to compress necessarily as well as other methods, like audio or images. This isn't used for image, but for things like text, it's great. It does pretty darn well. Okay, so the next topic we're going to do, which is actually, I'm very glad we ended this. The next thing we're going to do is information measures. And we're going to get into some really interesting stuff on not only sort of relationships between the entropic quantities, we're going to get into non-Shannon information measures. And this year I thought I wanted to spend like a lecture on talking about other measures of information like Renyi, entropy, and a few other interesting ways of measuring information. And then we're going to spend next week on that. And then after that, we're going to spend the rest of the time, I believe, on, if I'm not mistaken, on network information theory. So it's going to give us a good 2 weeks on that. So that will be the class. So I will then. So on Monday. By the way, this next material is in Raymond Jung's book. So it's not, the next bit of material is not in Cover's book. So if you want to read up in front before Monday's lecture, look at Raymond's book. It's actually a great book that I used once for this class. What was I going to say? Oh yeah, keep track of your email accounts for assignments, because I'm going to add some extra assignments about reading and stuff. So any questions? Okay, I will see you soon.